Hey everyone, welcome back to Chem Story. Today, we're diving into optical activity, a really important concept in stereochemistry. It's all about how chiral compounds interact with plane-polarized light, and this property is a big deal in organic chemistry, pharmaceuticals, and even biology. So let's break it down and see why it's so important. Before we dive into optical activity, let's take a quick look at plane-polarized light. It'll make a lot more sense once you check out the diagram, so take a moment to follow along. All right, let's keep going. Here's a quick look at how ordinary light turns into plane-polarized light. On the left, you can see a light source emitting ordinary light. The waves are oscillating in all directions. But once the light passes through a polarizer, only the waves oscillating in one plane get through. That's how we end up with plane-polarized light. The diagram makes this transition pretty clear and helps us see how light gets prepared for measuring optical activity. Now, here's where it gets interesting. When plane-polarized light passes through a chiral compound, its direction actually rotates. That's what we call optical activity. Let's take a closer look at the diagram to see how this works. All right, here's how it works. When plane-polarized light enters a sample tube containing a chiral compound, the molecules interact with the light, causing the polarization plane to rotate by an angle alpha. How much it rotates depends on a few things, like concentration, tube length, wavelength, temperature, and even the solvent. Once the rotated light comes out, it passes through an analyzer that measures how much the angle has changed. This rotation is a key feature of optical activity, and it's really useful in chemistry and pharmaceuticals when studying chiral substances. Optically, active compounds can rotate plane-polarized light in two different directions. If the light rotates to the right, we call it dextrorotatory, or D and plus. If it rotates to the left, it's levorotatory, or L and minus. Now that we know chiral compounds can rotate light, we need a way to measure and compare this rotation accurately. That's where specific rotation comes in. It provides a standardized way to quantify optical activity. The observed rotation can change based on factors like temperature, concentration, and sample tube length. Since these factors vary, specific rotation gives us a consistent reference to make reliable comparisons. To measure specific rotation, we used light with a wavelength of 589 nanometers. That's called the sodium D line. The light passes through a solution with a concentration of 1 gram per milliliter in a sample tube that's 1 decimeter long, or 10 centimeters. The measurement is taken at a specific temperature to keep it accurate. It's a standardized setup that helps us get consistent results. All right, to quantify optical activity, we use this equation. Alpha D equals alpha divided by L times C. Here, alpha is the observed rotation in degrees, L is the length of the sample tube in decimeters, and C is the concentration in grams per milliliter. This equation helps us compare how different chiral compounds rotate plane-polarized light under standardized conditions. Now, here's an interesting question. What happens if we mix equal amounts of two enantiomers? Let's find out. If we have equal amounts of both enantiomers, we call it a racemic mixture or racemate. In other words, it's a mixture that contains equal amounts of the two enantiomers of a chiral molecule. Since these two enantiomers rotate plane-polarized light by the same amount but in opposite directions, their rotations completely cancel out. That means the specific rotation becomes zero, and the mixture acts like it's optically inactive, just like an achiral compound. Even though the individual molecules are chiral, the mixture itself doesn't rotate light, making it look just like an achiral substance in terms of optical activity. But what if the mixture isn't perfectly racemic? If there's a slight imbalance with one enantiomer in excess, the cancellation won't be complete, meaning the mixture will still show some optical activity. To measure this imbalance, we use two important concepts: optical purity and enantiomeric excess. Both values are numerically the same in the same mixture, but they represent different things. Optical purity shows the degree of optical activity, while enantiomeric excess tells us the actual ratio of enantiomers in the mixture. Optical purity tells us how much optical activity a mixture has compared to a pure enantiomer. It doesn't directly give us the enantiomeric ratio. It's more about measuring the actual optical rotation. Unlike a racemate, which has a specific rotation of 0 degrees, Non-racemic mixtures have an imbalance between enantiomers, leading to a measurable optical rotation. Optical purity helps us quantify this imbalance in terms of optical activity, so it's really useful when analyzing chiral mixtures. Here's how the formula works. We take the observed rotation of the mixture, divide it by the rotation of the pure enantiomer, and then multiply by 100 to get a percentage. This percentage shows how much of the mixture's optical activity remains after canceling out the racemic part. It basically tells us the net optical contribution from the excess enantiomer. Let's look at an example with 2-bromobutane. The pure S form of 2-bromobutane has a specific rotation of plus 23.1. In a given mixture, the observed specific rotation is plus 9.2. Using the formula, we calculate the optical purity as 40%. So what does that 40% actually mean? First, it tells us the mixture isn't racemic. One enantiomer is more abundant. Second, it means that 60% of the pure enantiomer's rotation is canceled out by the racemic portion, leaving just 40% of the expected rotation. But keep in mind, this doesn't directly indicate the enantiomeric ratio. In other words, 40% optical purity doesn't mean one enantiomer makes up 40% of the mixture. Now that we've covered optical purity, let's move on to another key concept, enantiomeric excess. Enantiomeric excess tells us how much more of one enantiomer is present compared to the other in a mixture. While both EE and optical purity have the same numerical value, they reflect different aspects. EE focuses on the actual ratio or concentration of the enantiomers, rather than just the optical rotation. In short, it clearly shows which enantiomer is in excess and by how much. Enantiomeric excess is expressed as a percentage. To calculate EE, we first find the difference between the major and minor enantiomer amounts. Then, we divide that value by the total enantiomer content and multiply by 100 to get the percentage. In the formula, R and S represent the amounts or concentrations of the two enantiomers. This calculation shows how much of the mixture is made up of the excess enantiomer after canceling out the racemic portion, the part where both enantiomers are equal. For example, if we have a mixture with 70% of the R enantiomer and 30% of the S enantiomer, the EE comes out to 40%. That means 40% of the mixture is the excess enantiomer, while the other 60% is racemic, which cancels out in terms of optical activity. All right, that wraps up today's lesson. We covered optical activity, talked about optical purity as a way to measure a mixture's optical rotation, and introduced enantiomeric excess to describe the actual enantiomer ratio. The key takeaway? OP and EE might have the same numerical value, but they represent different things. OP measures optical rotation, while EE shows the enantiomeric composition. Understanding this difference is crucial when analyzing chiral mixtures. Hope this breakdown made things clearer. Thanks for watching, and I'll see you in the next lecture.